All right, this is the conclusion of Chapter 3, Section 3, the remainder and the factor theorems. The remainder theorem. Now remember, a theorem is a statement that we prove from geometry. Recall that. All right, remainder theorem. If the polynomial f of x is divided by x minus c, then the remainder is f of c. So we'll do a little proof of sorts, if you will. We're not going to do a two-column proof, but it's like a little proof here. Consider the division algorithm. F of x equals, here's my d of x, q of x, and r of x, right? This was my divisor, my quotient, and my remainder. If we evaluate this function at c, then every place we have an x, we replace it with a c, right? If we evaluate the function at f of c, we get c minus c times q of c plus r. Well, what does c subtract c equal? 0 times q of c plus r. Well, what's 0 times q of c? Well, that's 0 plus r. And 0 plus r is r. And so we do see that f of c equals r. And that's what this says right up here. If the polynomial f of x is divided by x minus c, then the remainder is f of c. Or f of c equals r. Now, when we're using the remainder theorem to find something like, in the next example, on the first example, actually on this page, it says, given this polynomial function, use the remainder theorem to find f of negative 4. Well, if the remainder theorem says f of c equals r, then my value of c must be negative 4. And then once I get what that remainder is after I use the synthetic division, I'm going to know f of 4 equals that remainder because of the remainder theorem that we just proved. Theorem is a statement that we prove, and we just proved it. All right, well, let's write here in our notes. I guess I'll use a different color. By the remainder theorem, if f of x is divided by x plus 4, then the remainder is f of negative 4. And if you look at the top of your page, it's just writing it that way. If the polynomial f of x is divided by x minus c, then the remainder is f of c. By the remainder theorem, if f of x, this polynomial, is divided by x plus 4, right? If c is negative 4, then the factor had to be x plus 4, right? We switch the sign when we put it back with x. Then the remainder is f of negative 4. Don't let this be tricky. Don't be that, like, what? No, it's not that tricky. You just take your actual, right, this is f of negative 4, this is f of c equals r, and you set up synthetic division. My c value is negative 4. And I look at my polynomial function, which is this right here, and I have to make sure I check the arrangement, right? 3, 2, 1, none. I'm not missing any terms. So I copy the coefficients 3, 4, negative 5, and 3. So I drop down On the diagonal, I multiply. I add. I multiply. I add. I multiply. I add. Folks, this is my remainder. And since I'm using the remainder theorem, f of c equals r, thus f of negative 4 equals negative 105. You know, we can verify this. Now, listen carefully. On an assessment, if it says use the remainder theorem, you must use synthetic division. The old way, which you're not going to use the old way to find the answer. All right, but we can verify this. F of negative 4. Remember the old way, I take the polynomial function 3x cubed plus 4x squared, subtract 5x plus 3, and I evaluate it at negative 4. And I could do this arithmetic on my calculator. You know, what's negative 4 cubed? 4 times 4, 16 times 4, 64. This is negative 64. Negative 64 times 3. This here. Negative 4 squared is positive 16 times 4 is 64. Plus 64. Plus 20, plus 3. Or plus 23. Oh, look at that. Negative 105. Negative 105. Okay, so this is just a different way of evaluating functions using synthetic division. This is verifying and using the old way. This is using the new improved, easier method. Okay, so just prove to you that in fact this did work. All right, if you have questions on that, please reach out so that I can help you. Let's take a look at the next page where we talk about the factor theorem. All right, the factor theorem. Let f of x be a polynomial. Okay. If f of c equals 0, then x minus c is a factor of f of x. Right? If f of c equals 0, right, 0 would be the remainder, then x minus c is a factor of the polynomial. And conversely, if x minus c is a factor of the polynomial function, then f of c equals 0. We could put this in and write a true biconditional statement, if you remember that stuff from geometry. All right, so this is here, proof again. All right, we're going to do a little mini proof of the factor theorem. Consider the division algorithm again. This is my dividend, this is my divisor, this is my quotient, that's my remainder. By the remainder theorem, the remainder r is f of c. So I'm going to replace this r with f of c. And I get f of x equals x minus c times q of x plus f of c by substitution. The first star. If f of c equals 0, then f of x equals x minus c times q of x plus 0, right? If f of c equals 0, I can replace f of c with 0. And I end up with f of x equals x minus c times q of x, right? If I have a product of two things, then they are factors of that original polynomial function. So we conclude that x minus c is a factor of f of x. All right, the second point, or the converse. If x minus c is a factor of f of x, then it must be true that f of x equals x minus c times q of x. Right? If we're saying it's a factor, we mean it divides it with no remainder. Replace x with c. We get f of c equals c minus c times q of c. And again, we see that this equals 0, right? F of c equals, well, this is 0 times that is 0. And that's what we have up here. All right, so again, if x minus c is a factor of the polynomial function, then f of x equals the product of these two factors. If I replace the x with c to find out what f of c is, then I get f of c equals 0. So it works forward and backward. All right. Let's now use the factor theorem. Now here's where, it's going to be really important that you read the directions so that you know what you're asked to do. In this particular problem, this says solve, and so you're looking for all the zeros of this polynomial function. Solve the equation, and S for solve, we're back to using set notation, so you got to put all your solutions or your zeros into set notation as your final answer. All right, let's read this. Solve the equation, here it is, equals 0, given that -1 is a 0 of the polynomial function. So what do we know? We know that -1 is a 0. We are given that f of -1 equals 0. So when I set up synthetic division, right, this is f of c equals 0, -1 in the half box. How many terms do I have? 3, 2, 1, none. I've got 4. This has to equal 0 right there. All right? They're telling us that -1 is a 0. We know that f of -1 equals 0. That's f of c equals r. The remainder has to be 0. All right? I'm going to put my coefficients here. You must use synthetic division for these. 15, 14, -3, and -2. Okay, drop it down. Multiply. Add. Multiply. Add. Multiply. And it does equal 0. Okay, so -1 is 0. So we're going to write here the remainder, 0. Verifies that x plus 1 is a factor of the polynomial function f of x. Okay, -1 was my 0 and -1 was my c value, but when I put it back together to figure out what is a factor of this polynomial function, I've changed the sign. All right, now we're going to put here, actually solve the polynomial equation. Again, the remainder 0 verifies that -1 is a 0, and x plus 1 is a factor of the polynomial function. The other polynomial that remains, these are my coefficients for it right here. Okay, it started out with a third power. This has got to bump down to a second. So this is 15 x squared minus x minus 2. And then what you do here to find the other zeros is to factor this. So I've got x plus 1. And you have to bring back your factoring skills. Remember, if this doesn't factor, then maybe there are no other zeros. Or maybe you can complete the square or use quadratic formula to find some zeros. That does happen with these problems. All right, factors of 15. Well, factors of 15 are 1 and 15 or 3 and 5. And being that this middle guy, the coefficient of it is pretty small, it's a 1, -1, that typically, how would you say, I'm going to use factors that are closer together, factors of 15. In other words, 3 and 5 are closer together on the number line than what 1 and 15 is. So I'm thinking this is 5x and 3x. Remember, the signs are different, and I'm going to subtract to get a 1. The only way to get 2 is 2 times 1. So if I put a 2 here, this gives me a 10 and a 3, and when I subtract them, I'm not going to get 1. But if I put a 2 here and a 1 here, well, that gives me 6 and 5. That works. So the 2 goes here, the 1 goes here. The larger product is negative, so 6x is bigger than 5x, so that's negative and that's positive. Almost done. I have to use ZPP. X equals -1. X equals, change the sign, divide by that, 2/5. X equals, again, I'm using zero product principle without writing it out. Change the sign, divide by what's in front of x is -1/3. We've solved equations before using the zero product principle. And so now I'm going to take these elements and put them into my set notation. -1, -1/3, and positive 2/5 are the zeros of this polynomial function. This is my solution set. Okay, so what did we do? They told us what a 0 was. We knew that was our C. We performed synthetic division. We verified it's a 0. You must have this part because you have to verify it. You then get a trinomial that you factor. Again, if it doesn't factor, then you use quadratic formula or complete the square. You could always post a question on the homework discussion if you're stuck. Now remember, when you do the homework, you got to check your answers. It's really important that you check your answers. All right, bottom here, number 1, number 2. If f of x is divided by x minus c and the remainder is 0, then c is a 0 of f. Let's look up here. C, -1, is a 0 of the function. And c is called a root. Remember, we talked about this before, roots and intercepts and solutions. Pretty much all basically mean the same thing. We could say or a solution, right? All right, if f of x is divided by x minus c and the remainder is 0 again, then x minus c is a factor of the polynomial function. we saw that x minus c, the remainder was 0, and so we conclude that x minus c is a factor. Okay. All right. One more example I think we have. You, if you would like, can pause the video and try that example on your own. It is an example where we are solving an equation. Remember S for solve, S for set notation. We're back to that again, getting solutions. Okay, solve the equation. If I know negative 1/3 is a root, remember this is the same thing as that's a 0. Okay, negative 1/3 is a 0. That's my f of c equals 0. So guess what? F of negative 1/3 has to equal 0. All right, I'm going to identify my c. Remember, when it's not grouped with x, you keep the actual sign. When it's grouped in with x, that's when you change the sign. And when you're putting it back in with x, that's when you change the sign. All right, let's check the lineup. 3, 2, 1, none. I'm not missing any terms. Now remember, you have to be careful to look for any missing terms, because this is going to occur sometimes. All right, I want to verify that negative 1/3 is a root, aka it's a 0. So here are my elements from my polynomial function. I'm going to set up for my synthetic division. I'm expecting to get a 0 here. If I don't, something's wrong. Drop the 3. Oh, so anytime you have a fraction times a whole number, just divide the whole number by the bottom and then multiply by what's in the top. Right? 1/3 of 3 is 1. This is negative 1. When I add, I get 6. Look, take the 6, divide by 3, you get 2 times 1 is 2. Or 1/3 of 6 is 2. And it's negative. Just got to be careful and watch the signs. This gives me negative 24. Right? 24 divided by 3 is 8. Negative times negative is positive. That's 8. And I do verify that it is, in fact, a 0. F of negative 1/3 equals 0 by the remainder theorem, right? And by the factor theorem, x plus 1/3 is a factor of the polynomial function. All right, so I'm going to write out x plus 1/3 times. Now remember, I have to use this, so we can't escape and not use the synthetic division because I need those elements to tell me what is in my next polynomial that I'm going to have to factor. This is 3 x to the power of, started out as cube. This bumps down to square, plus 6x minus 24 equals 0. You should be seeing what I'm seeing here. Hopefully you're seeing that there's a GCF. There is a GCF. So take the GCF out of this grouping. I'm going to pull it out front. Like way out front. 3. I'm going to copy this. And now I'm going to divide each one of the... Remember, I'm taking the 3 out of here, not here. And so I'm going to divide each one of these by 3. So I get x squared plus 2x minus 8. And that makes this more manageable to factor. 3 times x plus 1/3. Again, if this doesn't factor, you got to use quadratic formula or complete the square. Multiplies to 8, subtracts to 2. I can do that because the coefficient here is 1. The a is 1. 4 times 2 is 8, and when I subtract 4 and 2, I get 2. So I got x, 2, x, 4. Signs are different, larger product, 4x, the outers is bigger than the 2x. So this gets the plus, this gets the minus. There we have that in factored form. 3 is never a 0. Folks, this is a stretch, if you remember from graphing. All right, this is never a 0. Will never be 0. When would x plus 1/3 equal 0? When x is negative 1/3. Here, ZPP, x is positive 2. Here, ZPP, zero product principal, x is negative 4. So I've got 1, 2, 3 zeros. Don't mistake this. Please don't tell me that this is a 0. It's not a 0. And so my solution set, I put in set notation. I've got a negative 4, a negative 1/3, and a positive 2. And my equation is solved using synthetic division and knowing that negative 1/3 is a root. All right, if you have any questions, please post on the homework discussion, ask in class, or come to a Google Meet. Have a great day.